Hey guys, thanks for sending in your ideas. Several of you have been giving me suggestions of things that you want to go over, things that you maybe don't remember or just need a little brush up on. So far, I've got mass spectrometry, polymers, rate laws and elementary reactions, and periodic trends. Keep them coming because I'll be making videos and putting those up pretty soon. I'm also going to keep making these videos from time to time. And these are just walking through these big free response questions like what you're going to see. I figure if you've spent the last 3 or 4 weeks practicing AP free response questions, when it comes time for the real thing, you guys are going to be well prepared. So this one's from last year's AP exam, the released version, free response number 1. You can find the rubric there if you like, but I'm going to go through everything here and cover it all. And also, of course, I'll be giving you strategies and what to look out for with AP. So this first question here, we've got a little Lewis dot structure of urea. The first question says, what's the hybridization of the valence orbitals of the carbon atom in the urea molecule? So there's a carbon atom right there. There's only one of them. Now, identify the hybridization of the valence orbitals of the carbon atom, right? That's a lot of words, but this is just hybridization. And we have a very simple rule, right? If it's one thing on there, it's S. If there's 2 things, it's SP. If there's 3 things, it's SP2. And if there's 4 things, it's SP3. And that's really all you need. The shortcut works perfectly every time. So that carbon has 3 things stuck to it, so the answer here is SP2. All done with that one. This one's also not too bad as long as you remember what hydrogen bonding is. It wants you to draw one dashed line. There are lots of places you could write these, but remember that a hydrogen bond is always like this. I've got either a nitrogen, an oxygen, or a fluorine with a hydrogen attached to it, but you also need to have another one of those electronegative atoms to do the hydrogen bond. So you're going to form a hydrogen bond, right, using that hydrogen that's attached to an electronegative atom, and you're going to have to bond that too. And it could be any of these things, right? Here, I'm just going to put X here. It doesn't matter. X equals either fluorine, oxygen, or nitrogen. Has to be one of those 3 things. So find places like that. Look, the oxygens are this here. So that's an oxygen, 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 right? So I could make a hydrogen bond right there. I can make a hydrogen bond right there, right there, right there, right there. I could even go around this way there. Probably, some of the easiest places would be lots of different places here. Notice that every time I'm drawing my dashed line between a hydrogen, one of these guys, and either an oxygen or a nitrogen, one of these 2. That's where the hydrogen bond is going to be. And of course, the hydrogen has to be attached to either an oxygen or a nitrogen. There's no hydrogens attached to this carbon, so in this case, it's not really going to be a problem. Just make sure you got a hydrogen bonded to an electronegative atom. All right, so all of these are good examples. We could also do this. Tons of opportunities to get this right. The dissolution of urea is represented by the equation above. So it doesn't look like any dissociation happens. It stays a single particle, but it goes from a crystal to in solution to aqueous. The student determines that 5.3 grams can dissolve in water to make 5 milliliters of a saturated solution. All we have to do is calculate the concentration of urea in moles per liter, that's molarity, in this saturated solution. So I can get 5.39 grams, and I need that in moles. So this is grams of urea. I'm going to turn that into moles. 1 mole of urea is how many grams? It's right there, 60.06 grams of urea. So I've just rewritten this so that I can make the grams of urea go away and leave me with moles. So I do that calculation, and that gets me 0.0897 moles of urea. And I need moles per liter, so here's my volume. It's 5 milliliters, which is 0.005 liters. So I'm going to put that under my 0.0897 moles. Punch that in my calculator. I'm just going to take my answer that I already have, divided by 0.005, because that's my 5 milliliters. And that gets me, and I've still got 3 sig figs, so I'm going to go 17.9 molar. That's my concentration. So that's pretty straightforward. Student also determines that the concentration of urea in the saturated solution is 19.8 molar. So this was 20 degrees and this is 25. So at a higher temperature, I can dissolve more because this is 17.9, this is 19.8. So at a higher temperature, I can dissolve more. Based on this information, is the dissolution of urea endothermic or exothermic? Well, remember Le Chatelier, which is what this is talking about. I've got my solid. I'm not going to put the formula down. I'm turning that into aqueous, and I dissolve more, which means this reaction goes this way when I add heat. Remember with Le Chatelier, we said to think of heat as a reactant or a product. In this case, if the reaction goes to the right when I add heat, because it's a higher temperature, that means this has to be an endothermic reaction. If adding heat makes it go to the right, that's endothermic. If adding heat made it go the other way, it would be exothermic. So all you have to do here is say that adding heat drives the reaction towards the right, which means the reaction going toward the right has to be endothermic. When it talks about Le Chatelier, it's not a bad idea to mention the stress. AP likes to hear about the stress put on a system. In this case, we're heating it. That's a stress, and that stress is relieved by shifting the reaction to the right. All right, so this next question, it looks like a real pain in the butt, like you're going to be describing this huge experiment and everything. But then when you start reading this, you got to be careful. Make sure you answer the question that's being asked, because the question is really simple. The setup makes it seem like it's going to be a big, complicated lab description, but it's not. The equipment shown above is provided so that blah, 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 knowing the specific heat. So look, they gave me specific heat. What are the measurements that are required to do this experiment? So look, we've got urea. We're going to dissolve it in water in a polystyrene cup. That's our calorimeter. We did this lab. We didn't dissolve urea, but we did a calorimetry lab. We had the thermometer, the glass stir rod. There's our stir rod. There's our thermometer. We have weighed the exact amount of urea we put in there. We've measured the volume of the water we put in, but that also gives us the mass, and what we really need is the mass. And the two data points that we picked up were the initial temperature and then the temperature after the reaction was completed. And that's exactly what we need here. So all it asks you to do is list the specific measurements that are required. So we're going to need the mass of the urea. We're going to need the mass, which we could get from the volume, but what we need for the equation, right? Because remember, what we're doing here is Q equals Cm delta T. So they gave us C. This is the thing we're trying to find, right? Because it's the molar heat. And mass, we need, it's going to be the urea plus the mass of the water. So we need the mass of the water. And then delta T, so we need the initial and the final. So temp at the beginning and the temp at the end. That's what you need to get this question right. This is one point, this is the other. So the masses, that's one point, and the temperatures, that's the other point. And if you can just remember that this is what we're trying to do, you can figure out what data points we need. You also want to be careful. You see how it says molar heat of solution? So molar heat of solution is kind of a weird way of saying it. It's not the way we always used. We would say dissolution or of the reaction, something like that. But this is the thing that I've encountered in AP Bio and AP Chem so many times. This is really an attack on your confidence because they're trying to say things to you in a way that you maybe aren't familiar with. And that makes you think, I don't know what the heck's going on here. Now that's undermining your confidence, but you've got to remember they are trying to do that. Remember that your confidence is under attack. And so just let that slide and read the question and understand that I have taught you all of this. You know all of this. You have done and can do all of this. So don't let them try and shake you like that. Okay, you can find these things. If you don't understand what they're asking you for, see what you can pick up from context. See what you can pick up from word roots. Try throwing those words or phrases out of the question entirely because they're just trying to say things to you in a way that maybe you're not familiar with to make you think that you don't know what they're talking about, but you do know. They're just using different terms. So don't be shaken. Okay, so the entropy change for the dissolution of urea is 70.1 joules per mole Kelvin at 25 degrees Celsius. So that's the entropy change for the dissolution of urea. So that's the entropy change when you go from this to this. Now you could probably realize that it's going to be more entropy in the aqueous state than it is in the solid state because remember, entropy is just about the freedom of movement or the possible positions that it could go to, right? And if you're locked into a crystal, your possible positions, your freedom of movement is very limited. But when you're dissolved in a solution, you could be all kinds of places. So we're going to have an increase in the amount of entropy. So if this is how much it changes, all they're really asking you is how are we changing this number? Is it going up? Is it going down? Well, if we're increasing entropy, that's the amount of entropy we have in a solid. So we just need to add this. So it's just 104.6 plus 70.1, and that gets us 174.7. So the absolute molar entropy is 174.7, and we need the units on that, joules per mole Kelvin. So that's your answer for that one. Not too bad, it's just an addition problem. But you have to know that you're adding and not subtracting, and that takes understanding, right? So on the first day of AP Chemistry, I told you there are 3 things that you always have to be able to make these connections between. And if you look, most of these problems are all doing one of these 2 connections. So we're talking about what's happening at the particle level, what happens in the lab at the macro level, and then theoretically, mathematically, what's going on. So you've got to connect the math to the particle to the lab practical. Those 3 things. So many of these questions are just, how does this relate to this? How does this relate to this? How does this relate to this? And that's exactly what this is. Understanding the particle aspects of entropy and applying that to the theoretical or mathematical part. Here we are looking at particle level reasoning again. Why is delta S positive? So why is delta S positive when we go to dissolve it? I've actually already answered that, right? We just talked about that. Of course it was positive because we've got more freedom of motion. There are more possible positions for these particles to be in. You can't just write, they're flying all over the place. You have to say something like freedom of movement or particle position possibilities. The way AP likes it most of the time is possibilities of position. So when you're dissolved in the solution, there are a lot more possibilities of position. There's a lot more freedom of movement and therefore greater entropy. Last part here, part H, a student claims that delta S for the process contributes to the thermodynamic favorability for the dissolution of urea. So thermodynamic favorability, you know what we're talking about. That is our old friend delta G. That's our Gibbs free energy. So that's our thermodynamic favorability, right? Is it favorable? That's delta G. And it's going to be a negative delta G if it's favorable. And if you go back to Gibbs free energy equation, delta H minus T delta S. To be a favorable reaction, delta G needs to be negative. In this case, we have a positive delta S, which means this factor altogether there is going to be a negative value, which decreases delta G, meaning it's more likely to be negative, meaning it's more likely to be spontaneous. So you just have to say something like a positive delta S means a negative T delta S. And if I was answering this question, I would make sure I write down this equation to demonstrate. A positive delta S means a decrease in delta G, making it more likely to be thermodynamically favorable because a negative delta G is thermodynamically favorable. All right, so good questions on this one. You see how the 10-point question has parts from all over the place. That's what you're going to encounter, parts from all over the place like this. We start out with just hybridization, and then there was particle diagrams with hydrogen bonding, so intermolecular forces. There's simple stuff like solution concentration. We had Q equals Cm delta T. We had lab practical stuff, and then some thermodynamics for the last few points. This is what the question's going to be like. It's going to be a little bit of everything and spread out over these 10 points. But you guys got this. Keep doing these practices. Do them when I put them out. Don't save them for later. Love you guys.